Joe Liman, qui est un senior Rust consultant en Bootstrap et qui va nous faire un retour sur WASM et Rust.
Alors, je suis désolé que mon français n'est pas assez bon de donner cette présentation en français. Et merci pour votre flexibilité de parler en anglais. I won't subject you to my poor French anymore. So I'm this one, sorry, yes. I'm a consultant at Modus Create, which is a consulting company. We have an office here in Paris, and we have many other offices around the world. We do consulting in many things, but in particular, functional programming, Rust, OCaml, things like that. So, well, that's the wrong one. Okay. So I want to give a brief introduction to WebAssembly. I know we already had a talk about WebAssembly, but just very quickly. So WebAssembly, it's a this is a little smaller than I expected. I hope it's okay. It's a virtual machine. It's a kind of a language, an assembly-like language, also a sort of bytecode format for that language. You can think of it sort of like a Java virtual machine and a Java bytecode, but it has a few important differences. One of which is that there's no garbage collector, or at least originally there was no garbage collector. Very recently there was an optional one, but by default there isn't. It is completely sandboxed by default, unlike the other virtual machines. So if you don't do anything specific, then you cannot access the network in WebAssembly. You cannot access the file system in WebAssembly. The WebAssembly virtual machine can provide these to the WebAssembly if it wants, but by default there is none. As you might guess, or as you might know, or as you might guess by the name, it's supported in web browsers. Okay. It's also supported in other places, but it's in particular supported in web browsers. Here's a brief timeline of WebAssembly. So it was first announced in 2015, and it was released in 2017, I think around June, and then within a few months, I think by November, it was widely available, by which I mean it was available in all major web browsers. Now, of course, not all users of web browsers are on the latest version, but by now, I think more than 99% of all users of web browsers have WebAssembly available. So it's widely available. A few years later, it became an official WC3 endorsement. And so it's been around for, a little while now. When it was first released, there was a lot of hype. Okay, everyone was very excited about how WebAssembly was going to change the world. You'll see these are all things that were published in 2017, which was when it was first released. It was going to transform internet health. It was going to be the future of front end. It was going to be a revolution. It was going to lead to the fall of JavaScript. Kill JavaScript. This is my favorite one because, so remember, this was in 2017, so long-term means 2 years ago. Right? The Windows Store was going to drop support for non-WebAssembly apps. It was going to be dropped in Mac OS. Native Android apps would be gone, of course. So, obviously we know by now that this hasn't quite come about. So, as in any sort of new technology where there's a hype train, there was also a sort of disillusionment. Okay, something was holding up WebAssembly's adoption. In 2024, we heard that it was finally almost usable. Okay, it may have been overhyped. This is like a fairly common story of technology, right? There is a wave of hype, there's a wave of disillusionment, but also at the same time there are real applications. In amongst all this, up and down of emotions. So one of the well-known early adopters of WebAssembly was Figma, this company that makes the design software that runs in your browser. They were an early user, and they were very prominent in promoting how it was good for them. Another usage of WebAssembly that has been quite successful, I think, is for edge computing. So you have various edge computing providers that let you run your code on the edge, right? And the fact that WebAssembly is a sandboxed virtual machine is very good for them because you can run your untrusted code on their computers next to other people's untrusted code, and they're quite confident that it will run quickly and be secure. So Fastly, for example, is one company that offers this. Cloudflare also offers WebAssembly in their edge compute service. Okay, I'm sure there are others. These were just two examples. A third example where WebAssembly has found a usage is as a plugin language. So, for example, Red Panda is sort of a data framework, right? The database and data flows and all sorts of data stuff. And they allow you to define plugins in WebAssembly which run in the middle of Red Panda's code. Right? Again, because it's something sandboxed, it's something that they are confident that it will play nicely with their code. So here are some successes. I want to tell you about a project that I have been involved in involving Rust and WebAssembly. And I think it's interesting because the main thing that we got out of WebAssembly is maybe a little bit different from what people like to talk about. So let me get into that. This is a client project that we worked on at Modus Create. And I mentioned that so it's relevant for two reasons. The first is because it's a client project, I can't tell you sort of every single thing about it, but I think I can tell you enough things that to get the point across. The other reason I mentioned this is because it was a little bit experimental, right? I mean, one of the things that, when you're a company and you have your own engineers and you hire consultants, you're willing to give them something that's maybe a little bit more experimental because if it fails, then they can just fire the consultants and throw it all away. So that was maybe one reason that we were allowed to use a possibly experimental technology stack. Okay, I can tell you that the client that we were working with works with video and they work with machine learning on video. Okay, and I'll say a little bit more about that in a second, but first, just to give you an idea of the scale of the project, it was fairly small. Depending on the place we were in the life cycle, it had between 1 and 4 people working on it. So, okay, I'll put back the WebAssembly timeline here. We started here in June of 2022, and we completed the MVP. So this was a project that was used internally by the company. So when I say we completed it, I mean we completed it for their internal use about 4 months after we started. And we released sort of 1.0, where we finished the project about 6 months after that. Okay, and ever since then, it's been working, right? We've been maintaining it, it's been running, it's been successful. Okay. So this is the high-level view of our client's architecture. So they have a backend, and the backend is in charge of dealing with video in the cloud. So it has to store video, it has to ingest video, it indexes the video for easy retrieval, and then it retrieves it, and then it ships it. And it also does sort of video things like encoding and decoding and cropping and transforming and all that sort of stuff. Okay? And the client had 2 main classes of clients to this backend. On the one hand, we had machine learning clients, which were doing sort of video machine learning, and they were mostly written in Python. And they had to fetch video from the backend and then decode it and then do their machine learning stuff, right? And from the sort of architecture point of view, the interesting thing about the machine learning clients is that they have a very particular access pattern for data. When you play a video, you access it in a certain pattern. You get some video, you play it, you get the next bit, you play it, and so on. But the machine learning one is a little bit more random access. Right? It wants a frame here, it wants a frame there, in order to do whatever their algorithm wants to do. Okay? And then the other main class of users that we had were web. Okay. There was an internally used website which basically does monitoring for them and lets them sort of check on the performance of the machine learning algorithm and stuff like that. So it would need to access the backend to get video. It would need to display that video to the user. They had an already existing website that they were using written in JavaScript, and so we had to be compatible with that. And the web end, more than the Python end, was very concerned about performance because it was for interactive use. Now, the client had an architecture like this before we started the project, but they were unhappy with their implementation because, just as one example, their backend wasn't designed well regarding the web storage costs. They had astronomical storage costs. They wanted to rewrite it all. Well, they didn't want to rewrite it all. Sorry, they wanted to keep their existing machine learning users happy, and they wanted to mostly keep the work they had on the website, but they wanted to sort of revamp the backend and the communication. So here was our architecture. Basically, we wrote a Rust library, which would be shared between everything. So these blue things are our Rust library, right, duplicated in multiple places. We take that Rust library and we compiled it, and we put a native Rust application, which would be the backend. Okay, we took that same Rust library and we compiled it, and we wrote a little Python wrapper and distributed that as a Python library to their ML developers. And we took that same Rust library and we put a little bit of JavaScript glue around it, compiled it to WebAssembly, and shipped it to their web developers. Okay? And then after we'd done this, we realized it was also actually nice to have various command line tools for interacting with the backend for ops stuff and debugging and that sort of thing. And so we wrote those in Rust and also used the same shared library to implement that. Okay. Now, this talk is about WebAssembly in Rust, so I'm going to ignore most of it and just focus on this part. Okay, the technologies that we used in the WebAssembly part of our library include, we had to communicate with the backend, and maybe this wasn't the right choice, but we decided to communicate using HTTP. Okay, and so we used the request library, which is a well-known Rust library for HTTP, which implements a Rust native HTTP stack and so on. One thing that's interesting about it is that it actually has a pluggable backend. So when I usually think of request, I think it uses Hyper, which is the Rust HTTP implementation, but actually it's pluggable. And if you take request and you compile it for WebAssembly, then it will use the browser's native fetch API instead of the native Rust HTTP client. And that's very nice because it means that we could put our usage of request in our common Rust crate, which was compiled for everything. We could write all our logic that involved fetching and streaming and buffering and all that stuff using that shared crate. And we can use it everywhere, and it will use the backend that's appropriate for where we put it. So that was nice. In the browser, we used web codecs for decoding. This is a W3C draft spec. It's not supported in all browsers, for example, not Firefox, but because it's an internal application for the client, we can tell them they have to use Chrome. Okay, let's see, I don't think we need to say too much about that. We used asynchronous code quite heavily. Basically, it was very natural for us to use asynchronous code because, so first of all, the usage of video decoding, it's very convenient to be asynchronous because you hand a chunk of video to the browser and you say, decode it for me, and then when it's done, it gives it back. Right? So it's a very asynchronous interaction. You might have multiple chunks of video that you want to decode at once, so you have multiple sort of multiplex things going on. And the interaction with the JavaScript code is also tends to be asynchronous because the JavaScript code tells us we want to load video for these cameras and these time ranges and so on, and then we have to do our processing and get back to them when we have something. Right? So asynchronous code was very natural for us. We use Tokio quite heavily, which is interesting because Tokio, well, it provides a runtime, right? An asynchronous runtime. Which doesn't work on the web, right? It's a native thing, right? It uses platform stuff. But it also provides, in addition to the runtime, it provides lots of utilities. Like it provides channels, it provides locks, it provides, I don't know, stream combinators and all sorts of stuff, right? So we used a lot of that, but we didn't use the runtime. Instead, we used the WASM bindgen futures runtime, which is actually just a wrapper around the browser's asynchronous runtime, right? So when we're using asynchronous in WebAssembly, we I'll give you an example of what the code actually looks like. We write sort of normal Rust async, but then we ship it off to the browser's runtime, and it runs in the same asynchronous runtime that the JavaScript promises and so on are using. Okay? And what was nice about this for us is that, so obviously the WASM bindgen futures part is specific to our WebAssembly build, but a lot of the async code that we wrote actually lived in the shared library. It used the Tokio utilities, and then when we compiled it for native, it used the Tokio runtime. And then when we compiled it for web, it used the WASM bindgen futures runtime, but with the Tokio utilities. Okay, and so I've sort of already alluded to this, but one thing that was interesting about our stack, I think, is that we had various bits of it, which were shared with native. Various bits which were agnostic to whether you run it on WebAssembly or run it natively. And then we had other bits that were specific to WebAssembly, okay, which were only in the little wrapper that we put when we were compiling for the web. And there was really not much problem in having these things interact and coexist. This is just a quick example of what it looks like when you write Rust for WebAssembly. And what I want to emphasize is that I'm just showing you the bit that lives on the boundary, right? Like most sort of FFI sort of stuff, you have your Rust code, you have the JavaScript code, and then you have the sort of interaction glue. This is what the interaction glue looks like. So I want you to imagine that we have, does this work? Yeah. We have some struct called pixelclient, which I haven't defined for you, but I'm just defining the implementation of various methods on it. So you see all these annotations with WASM bindgen on everything. WASM bindgen is the name of the bindings generator that generates bindings between Rust and JavaScript. Okay, so we have to put these things everywhere so that it knows to generate code. Okay, now one of the things that's different between JavaScript and Rust is that in JavaScript you have constructors and in Rust you don't. So we have to tell WASM bindgen that this is the constructor for our object. Okay. And then it will generate a constructor in JavaScript so that when the JavaScript user says, give me a new pixel client, it will call pixel client new. Okay. The second example here I have is an example of what error handling looks like when you want to use it in the Rust JavaScript interface. And the thing about error handling is that they do it differently, Rust and JavaScript, because in Rust, you like to do your error handling with returning results, with a success case and an error case. Whereas in JavaScript, they like to handle errors by throwing exceptions if there's an error. And WASM binding is very convenient when it comes to errors, because what you get to do is you get to write the function as though it were a Rust function. And then WASM binding will generate glue for you, where if you return an error from the Rust function, then it will wrap that error up in an exception and it will throw it to the JavaScript. So you get to write your Rust code, like idiomatic Rust code, with using this question mark operator to propagate errors, and the JavaScript code gets to handle errors the way it likes to handle them by catching. Okay. And then the last example I have here is an example of what it looks like to have async code, not just async code running in WASM, but how it looks like to have async code interacting between JavaScript and Rust. And basically, this is an async function, but I don't get to write it as an async function. Okay, it's almost as good. I have to write it as a function which returns a promise. The promise is what JavaScript people call futures. Okay, and the way you construct a promise to return is you write your future, like you would normally write a future in Rust, and then you call this glue function, which is provided to you by the WASM binding futures library, which converts it to a promise. And then you return that to JavaScript, and the JavaScript developer gets to await it just like they would await a normal promise. Okay, and everything that you get to write in here just looks like normal Rust async code. So it's quite a nice experience. A little bit of glue code, but then on either side of the glue code, you really get more or less a native experience in both languages. Okay, but is it fast, right? So I told you that performance was important for us in this WebAssembly library. So what were the main points that contributed to our performance? Well, one of the big things for us was network transfers. Our usage of the network was very important. And this is common, I think, for web apps. The size of the app is an important component of how fast the experience is. Now, for us, the code size wasn't negligible. It was a negligible percentage of the network usage because it was a video app, right? So these people were loading our app, and then they were proceeding to download tens of megabytes, hundreds of megabytes, sometimes gigabytes of video. So if our app was twice as big as it should have been, who cares? We didn't even look at the size. Okay, one of the big computational costs that we had in our app was video decoding, because we had lots of video, some of it was quite high resolution, and it takes some time to decode all that video. But the video decoding for us was handled by the browser. It was handled by the web codecs API, and the browser decoder is presumably fast. It might even be hardware accelerated. We don't know. It's out of our hands. Okay, so whether we used JavaScript or Rust and WebAssembly for this, okay. Here's one place where we had success using Rust and WebAssembly. There was a period in this project where we had to do downscaling in software on the client. We would have preferred to do it in the backend, but there were like infrastructure reasons that delayed us from doing that. So we had to do software downscaling, and it was very easy. We wrote a very naive, for loop that went over the image and did some downscaling, and it compiled to very nice WebAssembly that even used, I think, SIMD instructions, and it ran very quickly in the browser, and we were happy. Okay. I can't honestly tell you how fast it would have been if we had done it in JavaScript. One little hiccup that we had in performance was caused by string copying and transcoding. So actually, we already heard, I think, that you pay a cost, when you have to transfer data over the interface between Rust and JavaScript, and it's an especially high cost when you do strings, just because of the annoying fact that in JavaScript they like to put strings in UTF-16, and Rust likes to have them in UTF-8. And so every time you pass them back and forth, you have to not only copy, you have to re-encode. Now you might think, well, we're doing video. How expensive can string transcoding be in comparison to decoding video? And you'd be right, except that you actually, it was a bit embarrassing when we first wrote it. We were doing so much string copying back and forth that you could actually see it in the profiles. So it's not too hard to work around, but you do have to pay a little bit of attention to how many strings you pass back and forth. Okay. Now I have a slightly off-topic story to tell you. 5 minutes? Okay, I think I have time to tell you the story. So this was a bit of performance that confused us a little bit, and I learned something from it, so I'm going to tell you, even though it doesn't have much to do in the end with Rust and WebAssembly. So we had some buffers that we needed to copy. Okay, and there were of various sizes, but the biggest ones were 12 megabytes, which is like not that big, but not that small. Right? And so we had to copy it, and we first tried to copy it using this function. Never mind the function; it's a whatever, something in the web API for web codecs. And this is a function which copies data from video memory into memory managed by a JavaScript array buffer. And it was taking us 8 milliseconds per copy, which was acceptable because this was the biggest buffer we had, and we were only targeting 30 frames per second video, so it was like, okay. But it was still kind of too slow, I think, right? So I did a quick calculation. My memory on my computer was like had 25 gigabytes per second of bandwidth. So if you work it out, it should take about half a millisecond. I'm sorry, half a millisecond, and it was taking 8. So we're like, okay, what's going on? We tried copying it in different ways. So one thing we tried to do was, well, maybe JavaScript arrays are just slow. So maybe let's copy it from video into WebAssembly memory instead. No, it's still 8 milliseconds. Okay, we're copying it from video memory, which could live on the graphics card if things are video accelerated. So maybe that's slowing us down. Why don't we try copying it from JavaScript to JavaScript? And it took us 8 milliseconds. And then what if we try copying it from WebAssembly memory to WebAssembly memory? And it took us 8 milliseconds. Maybe there's something going on in the browser. Maybe the browser is adding some overhead here. What if we try doing it just on native code? And it was still 8 milliseconds. Okay. So okay, at this point, as far as the performance of our web app goes, we could stop, right? Because it's not something we're doing wrong. It's not something to do with WebAssembly or JavaScript, right? And it's not a performance bottleneck for us anyway. But I wanted to find out anyway. So the long story short is that it's page faults. And I didn't realize this, but if you try and copy memory to a newly allocated buffer, like 90% of the time is servicing page faults. Servicing a page fault is so much more expensive than copying a page of memory that you spend all your time doing that. Okay. You can avoid this cost by reusing buffers or by upping your page size on your operating system. Anyway, turns out to be completely irrelevant for us, right? But, well, whatever. So there were some problems writing WebAssembly. One of them was that the Rust tooling for WebAssembly is a little bit immature. Until recently, there was no debugging support for WebAssembly in Rust. That was fixed about 6 months ago. There were some missing APIs, which we contributed upstream, so they're not missing, but there are probably other missing APIs. There's some issue with initialization, so this came up, I think, in a previous talk, of initializing the WebAssembly blob. It's a little bit annoying. Okay, whatever. There are also some ecosystem issues on the other side, on the web side of the equation. Bundlers, we found working with bundlers and WebAssembly to be annoying in a few different cases. There was this annoying thing with Sentry.io, which is a website for observability on the web, where whenever we had an error in WebAssembly, it would, for some reason, decide to upload the whole WebAssembly blob to Sentry.io, and quickly it used up our clients' quotas for Sentry.io, so we had to configure around that. Okay, the back traces that you get in the browser environment when you throw an error in WebAssembly are a little bit scary looking, especially to web developers, because you have these double colons and funny hex things and funny things like that. And the result was, no matter how good our error messages were, which are the error messages that we put there, the web developers would immediately contact us whenever they heard any of these things and say, it must be your fault, because look, it's some scary WebAssembly. So that was fun. Okay. So anyway, it was a successful project, I think. And what was good about it? Well, okay, what did we get good from WebAssembly? And I have an asterisk here because this is what did we get from WebAssembly in our project that was good. Okay, and the first thing that we didn't get was execution speed, because our execution speed was dominated by video decoding, and it didn't matter when we were doing things with WebAssembly. Okay, or there was also the memcopy, which was just like that's how hardware and operating systems work. Okay, we didn't gain from download size because again our download size was dominated by video transfer. We got to work in Rust. Which, okay, is that a good thing or not? Well, this is a Rust conference, so of course it's a good thing. But it won't convince the managers, right? So the big thing for us, was the code reuse aspect. And this is actually, we've seen it a couple times today. We got to write the same code. We got to maintain the same code once and use it in the backend, the web, the Python, the whatever CLI utilities. And I think that this reuse, this embeddability of Rust, together with WebAssembly, which allows it to be extended to web, is a really important part of the Rust and web ecosystem. And I think it doesn't get talked about enough. So thank you for listening to me talk about it.